Hi, John. Welcome to the Quantum Revolution.
Thank you, Antonella. I'm glad to be here.
So we're here today at Q2B, and I wanted to ask you a couple of questions. You obviously have a lot of experience in the field. You started being a student in physics and cosmology in particular. And then how was that like?
So I became aware of science in the 1960s when I was a kid because of the space race. You know, it was very exciting. We were going to go to the moon, and that ignited my interest in technology and scientific ideas. So I thought that was really what I wanted to pursue already when I was about 10 years old. And I felt, as a student, that the most exciting things in physics were the most fundamental questions about how matter works at a microscopic scale and what happened in the universe right after the Big Bang. And that was the focus of my research in the early years of my career. And then in the 90s, I got excited about quantum information. And that's been the main focus of my scientific work for about 30 years.
So when you make the switch, there were a couple setbacks in the physics theory thing.
Oh.
And is that why you made the switch, or?
Well, that's a psychological question. It's hard for me to give the definitive analysis. But I think what you're referring to is that for my generation of people doing particle theory, we were very excited about something called the superconducting super collider, which was the next generation particle accelerator that was already under construction in the United States. They had spent a couple of $1 billion digging a big hole in Texas where it was going to be. And we thought that was going to answer some of the questions that I had been curious about, you know, since the beginning of my scientific career. And that project was canceled in 1993 for political reasons. And it turned out it was going to take another couple of decades to have a machine that could explore some of that physics, which turned out to be the Large Hadron Collider at CERN. So I was doing some soul searching about, you know, what am I going to do now? And then I had developed an interest in quantum information, not because of quantum computing, which I did not see as promising in the early 90s. I was interested in black holes. I was interested in how they behave quantumly, what happens to information that falls inside a black hole. And that's how I became acquainted with some of the things people were doing having to do with how quantum information is stored and processed. And that prepared me, I think, so that when I heard about Peter Shor in 1994 discovering that, at least theoretically, a quantum computer could solve number theoretic problems like finding factors of large integers very efficiently, I was fascinated by that and wanted to understand it. And that steered me into quantum information. But my feeling then, and it's still my feeling now, is that what's really exciting to me as a physicist about quantum information is it's giving us a new way to explore nature and find out how nature works in a regime that we've never had access to before, namely when many particles are interacting quantum mechanically and enter a very complex state that we just don't know how to describe in the language of bits or the language that our computers understand or that humans understand.
That's very interesting, especially when you think about how, you know, we're getting more and more, humans are more and more tied to technology, and we're less tied to nature. So eventually, if we can have a technology that's more inspired by nature, then, you know, it could, in the way I think about it, could create a better world.
At Q2B, we are witnessing, and it's been true for years now, that there's enormous industry interest in quantum computing technology, which you can understand because it's a whole different way of doing information processing, and people understand that computation is important. But my feeling is that for a while, the main applications that allow us to do something new with quantum computing are going to be scientific. And whether they'll be commercially viable is less clear. That's okay with me. You know, the same thing happened with conventional computing. In the 40s, the 50s, people were excited about computers because they could solve scientific problems that people hadn't been able to solve before because they required too much computational power. And who could have said back then what we'd be using computers for right now? And I think the same thing will happen with quantum computing. The early applications will be scientific, but that's going to pave the way for applications that have a broader impact on people's lives.
Yeah.
I don't know how long that's going to take.
That's also a problem, is that, if for you, because you're a professor and you're doing research, it might not be a problem if for a long time the applications are things that you're interested in, it's scientific and you're learning more about black holes. But for people in the industry that are building startups and needing money to scale the hardware, they have to also sell potential applications that are commercially useful.
That's right. And we used to talk about the possibility of a quantum winter, that the high expectations would be frustrated.
Yeah.
And when the investment and business community got the impression that it was going to take longer for commercial utility to occur, that there would be a collapse in interest. I'm less worried about that now than I was a few years ago. I do think it's going to take a while, but I think we will make incremental progress, which will keep the field surging forward. Obviously, there are hundreds of startup companies, and they're not all going to succeed. That's the nature of startups. Many of them fail. I think the big companies that are investing aren't just going to say, okay, it's time to go home. They're going to see that the potential is there, and they'll want to continue investing. And for the big companies, the scale of investment now, although to physicists it seems enormous, is really not so big on this compared to, for example, the investment that's being made in classical machine learning and artificial intelligence.
Yeah, that's a big pull. Going back to the start of your career, there was a moment where you overlapped with Feynman, which is incredibly cool for someone that's in their 20s. And I was wondering, what were the talks like at that time about quantum information? Because he's the one that was talking about quantum machines. Did people think he was crazy, or,
Let me tell you a little story which is a little different than what you asked about, but it has to do with Feynman. It has to do with Feynman. So I told you back in, as a kid, I got interested in science and physics when I was about 10 years old. And one of the things that inspired me was a book which was called The World of Science, which described lots of different scientific fields. And the chapter that I found most interesting was about theoretical physics. And although they were not identified by name in the book, that chapter was based on interviews with Richard Feynman and Murray Gell-Mann, who were both Caltech physicists at that time. All the chapters of the book actually were based on interviews with Caltech faculty members. And that had an enormous impact on me. It was about how we're trying to understand surprising things about nature. Specifically, it focused on the rather amazing fact that the laws of physics look different in a mirror than they do in everyday life, what we call parity violation. And it just blew my mind. And it wasn't until years later that I realized that was based on interviews with Feynman. And so he had an impact on my life when I was 10 years old.
Wow.
And then, another 20 years go by, and I am his colleague on the Caltech faculty. You're right, it was pretty cool.
Yeah.
And Murray Gell-Mann was there too. He was another great physicist of that era. And so I overlapped with Feynman for 4.5 years. I arrived at Caltech in 1983, and he died in 1988. And we did interact a lot, but we never talked about quantum computing. I wish we had. We talked about other things. We were both interested in particle physics. So why didn't we talk about quantum computing? Because I didn't think it was interesting in the 1980s. In fact, I was steered towards reading a paper, which I can see in retrospect was very visionary, by David Deutsch, which came out in 1985. He described how we might be able to solve problems with quantum computers that would be too hard to solve otherwise. But I got the incorrect impression from reading his paper that he was really talking about what a computer scientist would call randomized computation, where in each step you flip a coin to decide what to do next. And I knew that wasn't so powerful. Yeah. And I thought, maybe this quantum stuff is just, fancy words for randomized computation. So I kind of dismissed it, and that was a mistake. So it really wasn't until Shor's algorithm was discovered that I appreciated there was really something to it.
And if in the 90s, you could have a time traveling machine, and John from the 90s that, didn't think about quantum computing really, walked the floor of Q2B today, what would shock you the most?
Well, one thing that, I don't know if shock is the right word, but having experienced it, there were two things that surprised me during that period. One was how rapidly the industrial interest ramped up at a time when I felt we still have a long, long way to go. And so for already, 10 years ago, and then at an accelerating pace for a few years after that, the companies were really taking it seriously all of a sudden, or seemed all of a sudden to me. That surprised me because I felt we still really have a long way to go to practical impact. Nevertheless, that's what happened. The other thing, which I guess you could say surprised me, was one of the things I've always been interested in is quantum properties of space and time. Like I said earlier, I'm interested in black holes, I still am, and things like that. And when I got started with quantum computing, nobody who works on those problems in what we call quantum gravity cared a hoot about quantum computing. But that actually changed. And we started to realize that ideas from quantum computing, including the idea of quantum error correction, is actually very useful for thinking about the quantum mechanics of space-time itself. So it was interesting to see that transition take place too.
Yeah, I'm sure. And about your first point, so you mentioned how fast the industry got interested in quantum computing. You initially coined the term quantum supremacy.
Oh, yeah.
And do you think that, being a leading professor, more scientific figure in the field, do you think that had an impact maybe?
Well, people started using the term.
Yeah.
Now, that originated in talks that I gave starting in 2011, and especially a talk at a Solvay conference in 2012. And I was talking to, in both cases, scientific audiences. And what I was trying to get across is this really is a very special time in the history of technology on Earth. Because for the first time, we're able, or will soon be able, it was still in the future then, to do things with quantum machines, that are just beyond the reach of what we could possibly do with conventional computing. And that's why I used, after thinking of other possible terms, I said supremacy, because I was trying to emphasize a big disparity between what quantum could do and what classical could do. Maybe it was an unfortunate choice of words, but anyway, unfortunate in two ways, because maybe it hyped things too much, but talking to a scientific audience, that seemed fine.
Yeah.
And also, the word supremacy is kind of politically odious, which I wasn't thinking about at the time. But it did have an impact. And, well, let me be clear. It wasn't a new idea, obviously.
Yeah.
It's what people have been talking about from the beginning, that we'd be able to do things with quantum machines that we couldn't do otherwise. What I was trying to say is, in the near term, they don't necessarily have to be useful things from a practical point of view. They're scientifically interesting. And even that wasn't a new idea. But it did, maybe it had some influence, yeah.
Okay. And you also coined the term NISQ, so noise intermediate scale quantum computers. What are and that's the era we're in right now.
Yeah.
What are the challenges of this era, but also the opportunities? Well,
so NISQ means noisy intermediate scale quantum. And actually, I proposed that term for the first time here at Q2B.
Oh,
and
wow.
in
I didn't know
December,
that.
yeah, it was the first Q2B, which was December 2017. And then I wrote up that talk and published it. And, it was called Quantum Computing in the NISQ Era and Beyond. And an important part of the talk was the and beyond. But I was saying, we're going to have this technology. It was 2017, so we weren't quite there yet. That will be able to do some things that go beyond what we can do with conventional computers. And so this will be a period of exploration to try to understand better what those things are, and in particular, if any of them are useful or have economic utility, because I was talking to a business audience. Yeah. But I also said that whatever applications there would be in my 2017 talk, they would certainly be limited because we wouldn't be able to do very large-scale quantum computations. They'd be beyond what we could simulate classically, perhaps, but still not nearly at the scale that we want for application. So we have to keep our eye on that transition that you're asking about from the NISQ era to what lies beyond, and that was going to mean using error correction. I'd been interested in this idea of quantum error correction since I first got into the field, and I worked on it in the 1990s. And at that time, we knew it was going to be important someday, but it was a ways off. I didn't mind that. I'm a theoretical physicist. I'm accustomed to talking about things that maybe people won't be able to do in the lab or on real devices for decades. In fact, I think that's important for people to do. But I was emphasizing that should be the focus, right? It's fine to try to see what we can do with these NISQ machines, because that's what we have. And of course, we'd like to see what applications they have. But let's not lose sight of the real goal, which is to make this transition to what we call the fault-tolerant era. And of course, we're in the midst of that now, so it's an exciting time.
Yeah, it's very exciting. And as for our quantum computing class, for example, this year, there's a huge emphasis on quantum error correction. And so I think, and even people at the conference, a lot of them are saying, oh, if you're a young professional, you should really look into quantum error correction.
I've been at Q2P every year since it started. And it's been interesting to see that in the first few years, everybody was talking about NISQ. And but with a few years ago, it started to tip towards general recognition that broad applications were going to require error correction. And, that seems to be widely accepted in the industry now.
Yeah. And so this morning in your talk, you said a few years ago, I wasn't excited about applications. Now I'm excited or interested. And I was wondering, so mainly because machines are getting better, and there's error correction, but also AI. Is that something that you think is also helping you get more interested?
Well, let me clarify that statement. Maybe I didn't state it well. You're referring to the talk I gave this morning to the Q2B audience. And what I meant was, I wasn't personally interested in running applications on the quantum platforms we had a few years ago. And I'm more interested now because I think they've reached a scale where they're scientifically more powerful. But what I have in mind specifically, and I mentioned it in the talk, is that for physicists, it's interesting to know what kinds of matter potentially could exist that we haven't discovered in laboratory experiments up to now. And that's what simulations on quantum computers can tell us about. And even for models of quantum matter that people have studied for years, in some cases because they're so hard to simulate with classical computers, there are properties that we just haven't been able to understand and compute, and our theoretical methods have limitations. And now we're getting to the point where we can start to learn some of those properties that are elusive for classical computers to a limited extent. We're really going to need error correction to go much further. So I mentioned in the talk that there are simulations of a lattice of fermions. Fermions are important for chemistry and for electrons or fermions for chemistry and materials. And we have models of fermions which are notoriously hard to simulate on conventional computers. That's where quantum computers could have an advantage. Still very small scale stuff, like a lattice of 36 electrons. That's already hard to do exactly classically. So we're at the stage now where we can compare running on a quantum computer to the best classical heuristics we have. And for the heuristics, we don't have a good way of characterizing how accurate they are. So comparing them to the quantum computations, I think, is interesting. Yeah. As now, you asked about AI. Well, obviously, AI is changing the world in a lot of ways, and quantum hasn't gotten to that stage yet. So combining quantum with AI is a topic that I'm interested in. I think we have a limited understanding of what the potential of quantum AI is because we theorists are trying to analyze it, with rigorous mathematics and say, okay, we can prove a theorem or something that shows this application is hard classically and it can be done quantumly. That's really hard to make convincing. If you look at what happened in classical computing, people just tried things and sometimes they worked. And that's especially true in AI. It's hard to be very concrete about what quantum AI will be able to do because we don't really understand why classical AI can do the things that it does. And, what made it finally work was scale, systems with enough processing. The theoretical ideas are pretty old, and people kept trying it, and suddenly, there was a moment when wide-ranging practical impact could be found. So I think with quantum AI, it may be similar. There are a few ideas which are not very well fleshed out from a rigorous mathematical point of view about how to combine AI and quantum. And eventually we're going to try those things, but we'll probably need error-corrected quantum computers to get to a scale where that'll be interesting.
Okay, so it's all very interconnected.
It's an exciting time.
Yeah. And say tomorrow you go back to your office and you find a NISQ machine. Which physics simulation problem would you want to run on it? And also, what modality would you want it to be?
I can answer that problem or answer that question in a somewhat more concrete way because we're actually using the machines in our group. And so remember, I have this background in particle physics. And so one of the things that I find interesting is using quantum computers to simulate particle physics phenomena, what we call quantum field theory. It's kind of the language of most of physics, including particle physics. There are some things that people have been able to compute with large-scale classical computations, some things that are just too hard. And the things that are just too hard are one example is dynamical processes. So, in particle colliders, you can bang together two protons at extremely high energy, and that produces lots of particles. People can't compute, can't predict exactly what will be produced from first principles, even though we know the right equations. It's quantum chromodynamics. We know exactly what's going on, or we think we do. And but it's just too hard to compute. But, that's an application of quantum computers in the long run. It might take a long time. But I think we can start to learn things about particle physics from doing simulations on quantum platforms before we get to the stage of doing, full-blown quantum chromodynamic simulation. So we've been thinking about that. We've tried to run applications on an IBM machine, and now we're going to try a Quantinuum machine. And at this stage, the classical methods are still better for the processes we're studying, but that's going to change. And we're going to see how far we can go with the machines that exist now, and maybe that'll point us toward things to try in the future where quantum advantage will really be scientifically informative.
And what about neutral atoms?
I think they're extremely promising. And it's quite an interesting story that, let's say we go back to when I first spoke at Q2B, when I was thinking about NISQ and what you could do with it. I was not thinking about neutral atoms in optical tweezers. It really was not on the radar screen of most of us. And people couldn't do circuits in neutral atoms. It was only maybe 4 years ago that for the first time, people were doing programmable circuits with atoms in optical tweezer arrays, and it's progressed very quickly. So now, actually, in one of my Caltech colleagues has a system with 6,000 atoms in tweezers, and work is proceeding to turn that into a processor. The fidelities are lagging a little bit behind now, superconducting and ion trap processors, but they're improving. And the fact that one can have thousands of atoms, and they're reconfigurable, so you're not limited by geometric locality, like in a typical superconducting processor, it's only the qubits that are nearest neighbors that can interact, on which you can perform a gate. And we're understanding that's an advantage for fault tolerance. So I'm expecting that the progress towards error-corrected quantum computing over some period of time is going to be led by the neutral atom processors. I'm not saying that's going to be the answer in the long run, but I think they're really ready to take off.
And they also use this. I was listening to a talk yesterday by Olivier Azrati, and he was mentioning like the energy going into the quantum processors, and it's one of the lowest ones as well. So that's important consideration.
And they're not very expensive to build.
Yeah.
The innovation that's occurred over the last few years, there are companies who are pursuing that technology, but the main innovations are coming from university groups. Yeah. It's very much modality, which is innovation driven. It's not, who can spend the most money. And you can have a few graduate students in a lab that's set up for a few $1 million, and they're doing state-of-the-art computations. So, if you had a lot of money, you could build 100 of those, and, if you wanted to.
Go crazy. And then towards the end of your talk, you mentioned good fortune for the quantum explorer, which I really like that phrasing.
Okay.
You've lived through the transition from a more like quantum information theory to now, the NISQ era, where the industry has picked up on quantum computing, there's machines being developed, and now we're moving to FTQC, so fault-tolerant quantum computer. What wisdom do you have for us to live through that transition? What?
Well, one thing I think it's really important to keep in mind is that this all came from fundamental curiosity-driven research. People trying to understand what's possible, trying to understand what nature can do. And of course, Shor's algorithm was immediately recognized as something that could have an impact on the world. But then the first processors were adaptions of technology that existed for other reasons. People were interested in superconductors because it was a way to explore quantum mechanics. And people were interested in trapped ions because it was a way to make a better clock. And those foundations had been set by research that was not aiming to be, commercially valuable. And I think that's going to continue to be true. I think in the grand scheme of things, we're still in the early stages. I'm not saying it's not exciting. It's really exciting now, and things are advancing quickly. But we still need a lot of innovation to realize our aspirations in quantum technology And we have to continue to nurture that fundamental research, because that's what's going to give rise to great technological opportunities further into the future.
Yeah. And it's hard to imagine what, the future will look like, but we tend to underestimate how fast technology evolves and can have an impact. For example, I was talking to my grandma recently, and she said that in the 50s and 60s, there weren't showers. You had a bucket to wash yourself. And I hope that's not just a Europe thing, because I will feel really bad. But thinking about a shower as technology for us is completely crazy, But it just, what kind of world, it's really hard to imagine, but, in 50 years, for example, what's the biggest difference that quantum computers can make?
Well, I don't know if you're asking me to answer that, but I guess your point is I can't.
Open-ended. Open-ended.
My point is, yeah, and I think it's always true that if you go to that type of time scale, 50, 100 years, we can't possibly imagine ways in which the world will change. But I think that's especially true when you come to quantum technology, because it's such a different way of dealing with information from anything we've been able to do before. Ways of storing it and ways of processing it, and also, detecting it. I think quantum, sensing technology is another interesting part of the story.
Brain interface.
Yeah, it's so different from what we could do before that we're especially limited in our ability to imagine the future.
Okay, is there anything else you want to say?
This has been fun.
Okay, thank you. Thank you.